Okay, I hope I'm audible to all students who are attending this lecture of econometrics. In this particular lecture, we intend to start with a new module within our lectures in econometrics. This is called instrumental variable estimation. Instrumental variable estimation. Okay, the book I prefer to follow for my lectures on this particular module, this is Econometrics by Jeffrey Woolridge. Econometrics by Woolridge. Okay, now let's first of all, understand what is going to be the aim of this particular topic, and what is exactly meant by an endogenous variable. And so we are going to look at all this. So if I quickly write, in this module, we will examine linear regression models. We will examine linear regression models in the presence of endogeneity. In the presence of endogeneity. Okay. Now, what is the situation of endogeneity? When does it occur? So remember, one of the assumptions we had made in our simple linear regression model was that the explanatory variables are not correlated with the error term in the regression. This was the assumption we had made. That assumption will get violated now. So I can write the situation of endogeneity. The situation of endogeneity occurs when at least one of the explanatory variables is correlated with the regression error term. Okay, so in case of endogeneity, the explanatory variables in our regression model, at least one of them, will be correlated now to the regression error term. So in that particular case, we have something called an endogenous variable, because that variable is dependent on the error term. So we are now going to see then what can we do in that particular regression model. What should be the estimation approach we should use, because we are going to learn that the OLS procedure, which we have been doing in the simple linear regression model, will not work now, because the OLS procedure works under the assumption that the explanatory variables in the regression model are not correlated with the disturbance or the population error term. But once your explanatory variables tend to become correlated with the regression error term, things are going to change. So let's now dig deeper into the topic. So let's write. So if I erase all this off, this was just a motivation or the aim. Let's now look at overview of endogeneity. Let me explain this using equations now. So overview of endogeneity. Okay, so recall that a key assumption we have used key assumption we have used when studying the simple linear regression model. When studying the simple linear regression model, remember our population regression function. Let me use the notations which Woolridge uses now. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 beta k x k plus u. This is my population regression function. It's a stochastic population regression function. And corresponding to it, the sample regression function, again, stochastic. The stochastic sample regression function is y is equal to beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 plus dot 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 beta k hat xk plus u hat. This is my sample regression function in the stochastic form. The key assumption was that, so if recall, the assumption we had made was that expected value of the population error term conditional on my regressors x1 to xk is equal to 0. Okay, so I can write this assumption which ensured the unbiasedness of OLS implied that the covariance of xj with u, which is my population error term, is equal to 0 for j taking values from 1 to k. This was the assumption we had made, that the expected value of the population error term u conditional on all my independent variables x1 to xk is equal to 0. And it was because of this assumption that we said that the covariance between the independent variable xj and the disturbance term u is equal to 0. In simple words, it means we had made the assumption that the disturbance term shares no correlation at all with the independent variables in my regression model. Okay, when I'm going to violate this assumption, we come to endogeneity. So I can write that is this assumption means that each regressor xj and the error term u should be uncorrelated. This is what this assumption means. They should not be correlated to each other. Okay, so I can say as soon as one of the explanatory variables xj becomes correlated, as soon as one of the explanatory variables xj becomes correlated with the population disturbance term u, the OLS estimators, that is the beta j's will be biased and inconsistent. They will be, I can write beta j hats. The estimators are always the hats. The beta j hats will be biased and inconsistent. So students, what we are trying to say here is, if at least one of the explanatory variables tends to be correlated with the regression error term, your OLS estimators will be now biased and inconsistent. That means beta naught hat will not be able to properly estimate beta naught. Beta 1 hat will not be able to properly estimate beta 1. Beta 2 hats from the sample will not be able to estimate beta 2, and so on. If one of the independent variables is now correlated with the error term. If that situation happens, that means if this assumption is violated, then your OLS estimators will be biased and inconsistent. Okay, so to make all students understand, let me take an example. So consider a simple example. Consider a simple example where I'm regressing, let's say, log of wage on beta naught plus beta 1 education plus my my disturbance term, population disturbance term u. So this is my population regression function. I'm regressing log of wage on beta naught plus beta 1 ed plus u. Okay, and corresponding to it, suppose my sample regression function for estimation is log of wage is equal to beta naught hat plus beta 1 hat education plus u hat. This is my sample regression function. Now, we know that the regression error term, u contains ability, which also affects wages. All students will agree with me on this. You can clearly see a person's ability to do work also determines the wages. A person which is more able to do work will be expected to get higher wages. But ability, I have not captured ability in the model. So since I have not taken ability as a variable, it is a part of my, since I have not taken ability as a variable explicitly, it's a part of my disturbance term or error term. And ability also depends on education. So they tend to be correlated. So I can write at the same time, we know that people with higher ability, tend to choose more education. People who are more able, who have higher levels of abilities, also tend to acquire higher levels of education. And thus, I can say that my explanatory variable, the explanatory variable education tends to be correlated with my error term u. So you can clearly see that education is no longer an exogenous variable. It is an endogenous variable, because education is dependent on ability, and ability is not captured in the model. So ability becomes a part of my regression error term u. So this u contains ability. And education tends to be correlated with ability. So education is correlated with U. So I can now write that as a result, the ordinary least squares OLS approach cannot correctly separate the effect of education on log of wage from the effect of the error U on the log of wage. If I run OLS for this particular regression model, if I run OLS, remember only after OLS I get the beta naught hats and beta 1 hats. So if I conduct OLS on this population regression function, it's not going to give me consistent and unbiased estimators, because education itself tends to be correlated with U. As a result, the OLS method will not be able to separate the effect of education on log of wage from the effect of U on log of wage. If education and the disturbance term were not correlated, then the OLS procedure would have been absolutely fine, because the impact of education on log of wage would be completely different from the impact of U on log of wage. But now, since education and U themselves tend to be correlated with each other, OLS will not be able to distinguish the impact of education on log of wage from the impact of U on log of wage. So if I show it, the impact of education on log of wage, which is the red, cannot be distinguished from the blue color, which is the impact of U on log of wage, because education and U themselves tend to be correlated with each other. The red impact cannot be distinguished from the blue impact, as you can see in the population regression function. So if I continue forward with the explanation, I can write that this will lead to bias and inconsistency. This will lead to bias and inconsistency in the OLS estimators, of both beta naught and beta 1. The OLS estimators of beta naught and beta 1 will tend to be biased and inconsistent. Okay, that is, I can say expected value of beta naught hat will no longer be equal to beta naught. Expected value of beta 1 hat will no longer be equal to beta 1. That means beta naught hat and beta 1 hat will be biased now. From in this example, beta naught hat and beta 1 hat will be biased. And inconsistent means that their variance is not going to, I'll say, they will not have the minimum variance among all other estimators. So they will be both biased and inconsistent in estimating beta naught and beta 1. Okay, so I hope students are clear till here. So if I erase all this off, so I can further write that by endogeneity, so we finally understand now that by endogeneity, we refer to any correlation between the regressors and the error term. Okay, so we will be using the following terminology. we will be using the following terminology. So I can write regressor xj, with the covariance between xj and u not equal to 0 is called an endogenous regressor. Will be called an endogenous regressor. And I can further write that regressor xj with the covariance between xj and u exactly equal to 0 is called an exogenous regressor. Is called an exogenous regressor. So I can say that if the covariance between the regressor xj and the disturbance term u is exactly equal to 0, which was the assumption made in the simple linear regression model, in that case, it's an exogenous regressor. But if that assumption is violated, if the covariance between xj and u is no longer equal to 0, that means if xj tends to be correlated with u, in that case, it's going to be an endogenous regressor. Okay, so I hope now all students are clear with this. And now let's quickly look at some of the OLS properties under endogeneity. So if I erase all this off, I can now write OLS properties. OLS properties under endogeneity. OLS properties under endogeneity. Okay, so I can say that we shouldn't be surprised. We shouldn't be surprised that our OLS estimators are bad. Bad means they're actually biased and inconsistent. They are biased and inconsistent if there is correlation, between the errors and the regressors. If the situation of endogeneity arises, if the error term tends to be correlated with the regressors, our OLS estimators will be bad. Bad means they are going to be biased and they are going to be inconsistent. Okay, so if you look at the regression model, so I can say in the regression model, yi equals beta naught plus beta 1 xi1 plus beta 2 xi2 plus dot dot dot. I can write beta k. It's a k variable regression model in general. So for this particular regression model, the first order conditions that define our OLS estimators are summation as I goes on from 1 to n. We have done this proof in our lectures in simple linear regression. Xij times ui hat is equal to 0 for all j taking values from 0 to k. Now remember, in my lectures, I have been using EI. So I can say that in my lectures, so here comes the notational difference. In my lectures on linear regression, I used EI, which I now replace by UI. Since I'm following Woolridge exactly, for my lectures on this particular module. The only difference is the notational difference. I have used EI before, but instead of, because I was using Damodar Gujarati at that time for my lectures on linear regression, but since for this particular topic, I prefer to use Woolridge. I'm just exactly following the book, so I can replace EI with UI hat. So remember, EI was the sample residual term, which was used to estimate UI. Now, instead of EI, I use UI hat. So we had proved. So check out my lectures. Check out my lectures on linear regression for the proof that summation xi ei is equal to 0 as I goes on from 1 to n. I have done this proof. The only difference is in the lecture today, we replace EI with UI hat. We replace EI with UI hat. That's the only difference. Okay. So when we had said that this is equal to 0, what was the assumption we had made? So I can say that the above first order condition makes sense. The above first order condition makes sense only if the expected value of xi ui xij ui is equal to 0. Remember, I goes from 1 to n, but j goes from 0 to k. J goes from 0 to k. However, I goes from 1 to n. Okay, so students should not get confused. I denotes the ith observation. And in totality, how many regressors do we have? We have k regressors from xi1, xi2 to xik. We have k regressors. So J denotes the jth regressor, I denotes the ith observation. I'm writing it here. Just for clarity, J denotes the jth regressor, I denote the ith observation. Okay, so do not get confused between I and J. So I can say that the above first order conditions make sense only when for the jth regressor, expected value of xij ui is equal to 0. For all j taking values from 0 to k. And equivalently, what does this mean? It means, or I can say, or equivalently, we all know it's nothing but the covariance. Covariance between xij and u is exactly equal to 0 for all j taking values from 0 to k. So the covariance between xij and ui, the covariance between xij and ui should be equal to 0. Okay, so remember the formula for covariance. If I erase the initial part. So first of all, I'm explaining the slide once again before I erase. We are looking at the OLS properties under endogeneity. What we learn is, if our OLS estimators tend to be correlated with the, if our let me correct myself, if our error term tends to be correlated with the regressors, our OLS estimators are bad. Bad means they are biased and inconsistent. If I look at a regression model, yi equals beta naught plus beta 1 x1 xi1 plus xi2 plus dot 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 beta k xik plus ui, where I denotes the ith observation, j denotes the jth regressor. J goes from 0 to k, I goes from 1 to n. The first order condition is defining an OLS estimator was the proof I have done in the simple linear regression. I had proved that summation xi ei is equal to 0 for the ith observation. Okay. Now the only difference is, instead of EI, since I'm using Woolridge, instead of EI, I replace it with UI hat, which is the estimator of UI. And instead of XI, I now write XIJ because I have J such regressors. This was for only one regressor. This was for only one regressor. Now I have k such regressors, capital K such regressors. So I can say summation xij ui hat is equal to 0. And this condition makes sense only when expected value of xij ui is 0 and expected value of xij ui is equal to 0 only when the covariance between xij and ui is equal to 0. Okay, now to show that, I am erasing the initial part of recall the formula, for covariance. So I can write recall the formula for covariance. So I can write covariance between xij and ui will be expected value of xij ui minus expected value of xij times expected value of ui. Now again recall, now expected value of ui is equal to 0. We know that the error term on an average will take the value 0. Sometimes it is going to take positive values, sometimes it's going to take negative values. And we had made the assumption in the simple linear regression model that the positive and the negative values on an average will cancel out, causing expected value of ui to be equal to 0. So this is 0. This is 0. So I can say that covariance of xij ui is exactly equal to expected value of xij ui. Because if this is 0, this whole term is 0. If expected value of ui is 0, this whole term is 0. So I can say covariance of xij comma ui is expected value of xij ui. And for the first order condition to make sense, covariance between xij comma ui, which we have shown is equal to expected value of xij ui, should exactly be equal to 0. Because only when the regressors tend to be uncorrelated with the disturbance terms, your first order conditions for OLS estimators are going to hold true. Remember the normal equations we had derived in the OLS estimators from the very basic lectures on simple linear regression. Those, normal equations hold true only when summation xij ui hat is equal to 0. And this happens, summation xij ui hat equal to 0 happens only when covariance xij ui is equal to expected value of xij ui is equal to 0. Okay, so I hope that students have understood this. Now, so I stop now in this particular lecture. The objective was, to introduce all students to the concept of endogeneity and what happens if what happens if the explanatory variables tend to be correlated with the population error term. We are going to dig deeper into the topic in the coming lectures as well. We have looked at how the regression model looks like in the presence of endogeneity. And we have also looked at the case that the OLS will not work now, because in case of OLS, if one of the independent variables tends to be correlated with the disturbance terms in the population, then the OLS is now going to give you biased and inconsistent estimators. The OLS estimators will be bad. So now in the next lecture, we are going to look at the solutions to endogeneity. In the next lecture, we are going to focus on the solutions, solutions to endogeneity, how we can solve the endogeneity problem. So I stop in this particular lecture. I hope students have enjoyed this introductory lecture for this particular topic. Any doubts in this lecture, you can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolofelconomics@gmail.com. This is where I stop in this lecture.